Electrical properties of solids. In this section, we will study about electrical properties of solids. Solids exhibit an amazing range of electrical conductivities extending over 27 orders of magnitude, ranging from 10 to the power minus 20 to 10 to the power 7 ohm minus 1 meter minus 1. So solids exhibit an amazing range of electrical conductivities, and these electrical conductivities are extended over 27 orders of magnitude, that is ranging from 10 to the power minus 20 to 10 to the power 7 ohm raised to power minus 1 meter minus 1. Here in the picture we can see a solid. Classification of solids on the basis of their conductivities. So let us learn about classification of solids on the basis of their conductivities. First type of solid on the basis of conductivity is conductors. The solids with conductivities ranging between 10 to the power 4 to 10 to the power 7 ohm minus 1 meter minus 1 are called as conductors. So this is the condition for a solid to be a conductor. Its conductivity should be in the range of 10 to the power 4 to 10 to the power 7. Metals are conductors, and they have conductivities in the order of 10 to the power 7 ohm minus 1 meter minus 1. And metals are good conductors because they have high values of conductivities. After conductors, next type of solids is insulators. These are solids with very low conductivities ranging between 10 to the power minus 20 to 10 to the power minus 10 ohm minus 1 meter minus 1. So insulators are those solids which have very low conductivities, and these conductivities range from 10 to the power minus 20 to 10 to the power minus 10 ohm minus 1 meter minus 1. Insulators are bad conductors, for example rubber and leather. And here in the picture we can see leather gloves which are insulators and are bad conductors of electricity. Conduction of electricity in metals. So here we will see how electricity is conducted in metals. Metals conduct electricity in solid as well as in molten state. So this is an important point here, that metals conduct electricity both in solid as well as in molten state. The conductivity of metals depend upon the number of valence electrons. So the conductivity of a metal is dependent on the number of valence electrons. Higher the number of valence electrons, higher is the conductivity. In metals, the valence band is partially filled, or it overlaps with higher energy unoccupied conduction band so that electrons can flow easily under an applied electric field. So in the case of metals, valence band is partially filled, or we can say that the valence band overlaps with the conduction band. And overlapping of valence band and conduction band facilitates the flow of electrons under the applied electric field. So conduction in metals takes place due to the movement of electrons in the conduction band under the action of the applied electric field. And here in our picture, we can see articles made up of metals. This is an aluminum foil, and here we have a copper coin. Both are metallic and are good conductors of electricity. After understanding the case of metals, let us look at the energy band diagram of insulators. In case of insulators, the gap between the valence band and the next higher unoccupied band is large, so that electrons cannot jump from the valence band to the conduction band. So this is the energy band diagram of an insulator, and here we can see that energy gap between the valence band and the conduction band is quite high, and this energy gap is known as the forbidden gap. So due to such large gap, electrons are not able to jump from the valence band to conduction band and constitute conduction of electric current. After having studied about conduction of electricity in conductors and insulators, let us learn about conduction of electricity in semiconductors. In case of semiconductors, the gap between the valence band and the conduction band is small, so some electrons may jump to the conduction band and show some conductivity. So in case of semiconductors, the gap between the valence band and conduction band is small, and that is why some electrons may jump from the valence band to the conduction band and show some conductivity. So here we can see the energy band diagram of a semiconductor. This is the valence band and this is the conduction band. And the forbidden gap is quite small in the case of a semiconductor. That is why some electrons are able to jump from the valence band to the conduction band and constitute conduction of electric current. Electrical conductivity of semiconductors increases with rise in temperature, since more electrons can jump to the conduction band. So this is an important point regarding electrical conductivity of semiconductors. Electrical conductivity of semiconductors increases with rise in temperature. So as the temperature increases, there is rise in electrical conductivity of semiconductors as more electrons can jump to the conduction band from the valence band. After learning about electrical conductivity of semiconductors, let us learn about intrinsic semiconductors. Those semiconductors which are so pure that impurities do not affect their electrical behavior are called as intrinsic semiconductors. So what are intrinsic semiconductors? Intrinsic semiconductors are pure semiconductors, and impurities which are present in them are so small that they do not affect the electrical behavior of the semiconductor. Such semiconductors are known as intrinsic semiconductors, and examples of intrinsic semiconductors are silicon and germanium. They are dominated by number of carriers, which increases exponentially with increasing temperature due to increased probability of electrons jumping across the band gap. So intrinsic semiconductors are dominated by number of carriers, and number of carriers increases exponentially with increasing temperature due to increased probability of electrons jumping across the band gap. Band gap here means the forbidden gap between the valence band and the conduction band, and silicon, as we have learnt, is an example of an intrinsic semiconductor, and here we can see the picture of pure silicon. After learning about intrinsic semiconductors, let us see what is the meaning of doping. Process of adding an appropriate amount of suitable impurity to increase conductivity is called as doping. So what is doping? It is the process of adding an appropriate amount of suitable impurity to increase the conductivity of the intrinsic semiconductor. This process is known as doping. It can be done with an impurity which is electron-rich or electron-deficient as compared to the intrinsic semiconductor such as silicon or germanium. So doping can be done with the help of an impurity which is electron-rich or electron-deficient as compared to the intrinsic semiconductor silicon or germanium. Here we have a picture of doping. Here we can see that in the germanium crystal, an impurity of arsenic has been added. And arsenic has 5 valence electrons as compared to 4 valence electrons of germanium. So here we can see that the impurity is electron-rich as compared to the intrinsic semiconductor, which is germanium in this case. We have learnt about intrinsic semiconductors, and we have another type of semiconductors which are known as extrinsic semiconductors. Extrinsic semiconductors are produced from intrinsic semiconductors by the process of doping. So when impurities are added to the intrinsic semiconductors, extrinsic semiconductors are obtained. And here we have types of semiconductors. So extrinsic semiconductors are of two types. The first type is N-type semiconductor. In N-type semiconductors, conductivity increases due to negatively charged electrons. So in the N-type semiconductors, the conductivity increases due to negatively charged electrons, and they are generated due to the doping of crystal of group 14 element such as silicon or germanium with a group 15 element such as phosphorus. So here we have an important point that N-type semiconductors are produced when crystals of a group 14 element such as silicon or germanium is doped with an impurity from the group 15 element such as phosphorus. So in simple words, when in silicon or germanium impurity of phosphorus is doped, then we have N-type semiconductors, and here we have pictorial representation of formation of N-type semiconductors. And in this picture we can see that this is the crystal lattice of silicon, and here we have the impurity of arsenic, and in arsenic we have 5 valence electrons, out of which 4 electrons are used up in bonding and 1 valence electron is left free. Due to this free valence electron, conductivity of the semiconductor is greatly increased, and because here we have excess of negatively charged carriers, that is why this type of semiconductor is known as N-type semiconductor. After N-type semiconductors, the next type of semiconductor is P-type semiconductor. Under the influence of electric field, electrons would move towards the positively charged plate through electronic holes. But it would appear as if electron holes are positively charged and are moving towards the negatively charged plate. So under the influence of electric field, electrons move towards the positively charged plate through electronic holes. But it appears as electron holes are positively charged and are moving towards the negatively charged plate. So in semiconductors, we have two types of charge carriers, electrons and holes. Electrons are negatively charged and holes behave as positively charged carriers. Electrons move towards the positive plate and holes move towards the negative plate of the applied electric field. This type of semiconductors are called as P-type semiconductors. So those semiconductors in which the majority charge carriers are holes are called as P-type semiconductors. In P-type conductors, conductivity increases as a result of electron hole. So here we have a diagrammatic representation of P-type semiconductors. P-type semiconductors are formed when silicon or germanium crystal is doped with trivalent impurities. And these trivalent impurities can be of boron and indium. So here we can see the silicon crystal lattice, and this is the impurity atom which is trivalent. In the diagram we can see that each atom is bonded with 4 other atoms, but trivalent impurity has only 3 electrons. So in order to complete the bonds, this impurity robs 1 electron from the nearby bond and completes its 4 bonds. In this process, here we can see a vacancy of electron is created, and this vacancy of an electron is known as a hole. Now this is the second type of extrinsic semiconductor, which is P-type. So from here we can learn that extrinsic semiconductors are of 2 types. N-type, in which electrons are the majority charge carriers, and P-type, in which holes are the majority charge carriers.